Alright, so the first one. We'll look at the limit as x goes to infinity of 1 over x to the 1 over x squared. So if I try to plug it in, what do I get? It'd be 1 over infinity to the 1 over infinity, right? And 1 over infinity is the same as 0. Alright, so we get 0 to 0. What does that mean? Do we know the answer yet? No, this is one of 3 indeterminate forms where we have a power. It's like 1 to the infinity, 0 to the 0. We don't know what the answer should be. Why is this one indeterminate? Think about what is 0 to the 5 power? 0. What's 5 to the 0 power? 1. Should this one be 0 or 1? 0 in the base, you want to say 0. 0 in the power, you want to say 1. Is there any way to make a choice here? Which 0 matters more? So that's why it's indeterminate, right? So what can we do to solve this problem? Yeah, so logarithms. So can I just randomly take the log of something? Why would we want to do a logarithm? Yeah, so we kind of learned this with logarithmic differentiation. The idea that when you take the log, anything in your power moves out in front becomes multiplication, right? So it's nicer if we have a log sitting here, but then can I just randomly take the log? I really don't want to change the problem. So the idea is this is the same as e to the natural log of this. When you do e to the natural log, they don't do each other, right? So did I change the problem? And I just wrote e to the natural log on the outside. Technically, that assumes this is a number greater than 0, otherwise you can't do this. We'll ignore that fact. Alright. So there's one kind of nuance here. It's an assumption we're going to make. We always do this. We can run through this trick. Mathematically, there's some technicalities. But we always replace this with e, then move the limit to the outside. So instead of taking the limit first, we want to take the log first. Why do we want the log first? Can I use the log count property here? My log's not acting on something to a power, right? It has this limit thing in the way. So I really want to interchange these two. I want to put the limit on the outside with the log on the inside. Anybody have a guess of why we're actually allowed to do that? This one's kind of subtle. Because the logarithmic function is continuous. What does it mean to be continuous? It means if you want to take the limit, you just plug in, right? So if I want to take this limit, it would be the same as just plugging in this value. I can move the limit to the inside, or I can go the other direction. So it's a continuity path. We never tell you just how that or anything. We're just going to use this to find answers, but there's a reason behind it. If you look in the book, the first thing they do, which I don't love, is they say, solve this problem, and then at the last second, write e to the answer. So they do just randomly take a log and then solve everything, and then remind you, oh, whatever answer you get here, you need to put e in the power or in the base, which is completely random. So the way I like doing this is you maintain equal signs. To maintain equal signs, I just do e to the natural log on its own. So I always have the e sitting there so I don't forget it. Right? The book does solve a different problem and then put it together at the very end if you're reading the book. In the videos and notes, we always do it this way just because it's consistent. Alright, so what's the next thing I do? Why did that so I haven't really done anything, right? I just rewrote the problem. I haven't used any log properties. So the log properties say I can move this 1 over x squared outside the power, or outside the logarithm. Right? So now, what kind of form do I have? So for the rest of this problem, this e is sitting here. And then the power would be 1 over infinity times natural log of infinity. What's 1 over infinity?
0.
0. What's natural log of infinity? Infinity. So what's the difference now? Before we had 0 to the 0, now we have 0 times infinity. Do we know the answer yet?
No.
When you multiply by 0, what should your answer be? 0. When you multiply by infinity, what do you think your answer should be? Infinity? Do we know which one wins?
Couldn't we put the ln of 1 over x as the numerator for the, and then...
Yeah, we're gonna rewrite it now. So what's the rule? We kind of talked about this on Friday. It's a long time ago. All this is in the section on L'Hopital's rule. Have I used L'Hopital's rule yet? When are we allowed to use L'Hopital's rule? Yeah. It has to be indeterminate, which all these are indeterminate, but then it has to be a fraction. It has to be 0 to 0 or infinity divided by infinity. So what do I need to do now? I have 2 things multiplied. I need to write it as a division problem. How can you do that? Basically, I need to move 1 to the bottom, right? Then you can't just move it, you have to move it as a reciprocal. So instead of multiplying, you divide by the reciprocal. Or because you look at this problem long enough, there's actually a natural one to move without, or a better way to write this problem. I said, this is what you were saying, I have 1 over x squared here, then natural log is something here. Why do I have the natural log, or why am I doing this times this? I could easily just put divide by x squared, right? So I kind of have one sitting there ready to move already. This is e plus limit of natural log 1 over x divided by x squared. Technically, you could say divide by 1 over x squared. Or divide by 1 over 1 over x squared, which becomes divide by x squared. You are technically doing that, but or you can just say, hey, instead of multiplying by 1 over x squared, that's the same as dividing. Just go ahead and move the division part. Right? Why would I do this? Now what do I have? So we said this is natural log of 0 plus over infinity. What's natural log of 0 plus? We're hitting every one of these. Hey, y'all. What is 0 plus here? Which makes that minus infinity. Natural log of this. Alright, so now I have e to the negative infinity divided by infinity. I finally had this fraction where it's infinity over infinity. All of that was just to rewrite the problem so that I could start using some other tricks. Why would I think to do this? I mean, there's nothing I can just factor here, right? Like, I have no other great way to do this. What did we learn when we have x's in the base and x's in the power? You need to do a change of base type idea. When I did change the base, I put e in the base, and now all the x's are only in the power part. So it makes it look nicer. Alright? So now I can finally use L'Hopital's rule. I finally have a fraction. So what does L'Hopital's rule say? Actually, there's one other one. I know I need to take the derivative, right? You don't need to do this, you can just take the derivative. What do I get on the top? minus natural log of x over x squared. Am I allowed to do that? This isn't one I necessarily expect you to do. You could just take the derivative. But if I'm taking a derivative of a log function, sometimes we can clean it up first. Why would I do this? E to the limit as x goes to infinity of natural log of 1 divided by x squared minus this limit. Why would I care? What's natural log of 1?
0.
Okay, go back to the graph. When's it cross the x-axis at x equal 1? So technically this is e to the 0 divided by infinity minus this limit. What's 0 divided by infinity? What's 1 divided by infinity?
0.
And then you multiply by 0, what does it say? 0. So this would be e to the 0 minus this. So I did a bunch of work, basically to say this is the same as this limit. Alright. Which is still what form? E to the minus infinity divided by infinity. Like I didn't change the form, I just rewrote it to make it look tough and easier. I'll redo this one the other way, so you don't see it. Or instead of doing this. Alright, so I still have a fraction. L'Hopital's rule says to do what? Instead of taking the limit of this, what do I take the limit of? Ratio of the derivatives. Take the derivative of the top, take the derivative of the bottom. Right. What's the derivative of the top?
1 over x.
1 over x. What's the derivative of the bottom?
2x.
2x. You can write the extra step in there where you write dx so you know what's going on. Or you can just take derivatives as you go. That circle H tells me I know what happened there. Those are the derivatives. Yes?
Doesn't that turn into 1 over 3x? Doesn't that turn into 1 over 3x?
Turn into, I'm sorry?
1 over 3x.
Almost.
Oh wait, no.
Not quite. So what would this be? 1 divided by x divided by 2x. This is where it's really easy to make simple mistakes. Really, it says start with the 1 on top, move the x to the bottom. So what would I get if I move the x to the bottom?
2x squared.
2x squared. Now what should I do? Do I have infinity over infinity form anymore? No, I'm just not trying to plug in. After you do something, I always try to plug in and see what you have, right? 1 over 2 times infinity. What's 2 times infinity? Still infinity. So what's 1 over infinity? 0. So we get e to the minus 0. Say e to the 0. And what's e to the 0?
1.
1. Did a lot of work to eventually get to the answer we want. I mean, these are advantages. You have to move multiple things. There's lots of pieces. So the trick is always being, as organized as possible. Remember why you're doing this. What could I have done here? If I didn't want to rewrite this, I could have just taken the derivative directly. So it's been L'Hopital's rule. Now I need the derivative of natural log 1 over x. That's 1 over x times the derivative of 1 over x, all divided by 2x. So 1 over x is just x times derivative of x to the negative 1 power. So that's x times negative 1, x to the negative 2, divided by 2x. And now when you clean it up, there gives me a negative sign on top, x over x cancels, 1 over 2x squared. I got the same thing, right? I could have just taken the derivative directly, but because there's a log, sometimes you can clean it up. You don't want to forget some of those derivative rules that are sometimes. So that one, the derivative was more work. And I did the same amount of cleanup in some sense. So then it's just decide which one you prefer, or be consistent. Just make sure you're not like skipping rules or skipping steps. Any questions on that one? I think there's 3 of these in the homework, so. Always make sure L'Hopital's rule applies. Don't just start using L'Hopital's rule. I mean, that's where it's the easiest way to lose points. On the quiz, there will just be find the limit problems. And there will be at least one where you don't want to use L'Hopital's rule because it's not a fraction where you can get the right indeterminate form. Part of knowing L'Hopital's rule is knowing when not to use it. So it helps a lot of the time, but there are times you can't use it. Sorry. All of this work that we did up until this point was just so we could use L'Hopital's rule. Any questions? How many of y'all are, oh, yeah.
So up there, you put like the equals with the H in a circle, but then in the book it says like do L apostrophe H.
Either way is fine.
Okay.
It's just some notation to let you know how you went from the line above it to the next line, because if you just look at the formulas, they seem random. Like you might not see it as the derivative. You can also just take the derivatives. I mean, there's that I don't count off for. Even on the prac problem, I probably wrote H and circled it or something if you didn't make any notation. I didn't count off for that. It's more of I recommend making some notation so you know what's happening here. But as long as everything's equal there, that's fine. All right, how many of y'all are computer science majors? All right. We're going to play favorites and talk about a topic that I was going to skip. What does it mean to say F dominates G? We'll say as X goes to infinity. It's not always as X goes to infinity. You could say X goes to 0. But what does it mean to say one function dominates another function? You do this when you do big O notation. So think about all your sorts. When you do merge sort versus bubble sort and all the other ones, you basically talk about how many steps it takes. Binary search.
Yeah, F has a higher, bigger effect on the final complexity than G does as it scales with size.
Yes. So it doesn't matter which one you put on the top. When we say F dominates G, you mean F is a much bigger function. So if F is a lot bigger, what would happen if you take the limit as X goes to infinity and divide these? If it's significantly bigger, it goes to infinity. What if F is significantly bigger and you divide by it?
Goes to
This limit
0.
should be 0. Also make it where there's non-negative, make them positive. What does it mean for one to be significantly bigger than the other? It means if you took the ratio and took the limit, the bigger one wins. This one goes to infinity, therefore this goes to infinity. So we're again assuming both of these functions might go to infinity. How do you know which is the bigger one? Take the ratio. If one wins in limit in this ratio, so both of these might go to infinity. If this still goes to infinity, it means this one is significantly bigger than this one. If it goes to 0, it means this one was significantly bigger than this one. The other one would be, what does it mean for f equal big O of g? This means they're basically comparable. So how would we say that? If you take the limit as x goes to infinity, f of x over g of x. These are in the book. This one's technically not in the book, so we have to be a little careful here. But what it says is this is a constant where 0 is less than c less than infinity. So if this ratio goes to a tie, or when do we call it a tie? If this ratio converges to a number. What does it mean if they're a number? So think like x squared and 2x squared. Who cares if the coefficients all by 2? They both behave like x squared, right? So this is like when you do all the sorting algorithms and you compare them. What does it mean to be big O of the other one? It means they behave roughly the same. And it's up to a constant here when you take limits. Technically, this is painful for me to write. Technically, you need something like this. And this. If you want to do this precisely, this limit may not exist. So in here, the limits always exist. In reality, limits may not exist. But then what this notation means is take the biggest upper bound, it must be bounded by a constant. Take the smallest bound, it must be bounded by a constant. And this constant can't be infinite or 0. So there are some technicalities there when you say big O. But that's one of the topics that shows up in this section. And the example is, what if you take f of x as x to the cube, or x cubed, and g of x equal e to the x. Which one do we think is bigger? If you were to invest your money, do you want to pay like e to the x or f of x?
It scales exponentially, so I think it goes higher, faster.
Okay. Okay, even bigger. You're making an investment. Do you want your investment to grow like f of x or g of x? F of x is going to be bigger early on. But which one eventually wins?
E to the x.
G of x. Exponential growth always beats polynomial growth, which is one of the big ideas you talk about in computer science. Whenever you do any of these algebra analysis. How do we see that? So it doesn't matter which one you put on top, because if this goes to infinity, this one must go to 0. So either way, these are really saying the same thing. So pick one, put it in the top. So this is this divided by this, which is infinity over infinity. Can't find that limit, so what do I do? It has the right form for L'Hopital's rule. Still infinity divided by infinity. So we L'Hopital's rule again. Still infinity divided by infinity. But I'll do it one more time. I get this. Now what happens?
The e to the x wins.
I get this huge number, but I divide by infinity. E to the infinity is infinity. Which means this goes to 0, right? So what does that mean? That means my exponential function eventually grows significantly faster than my f of x function. And technically you can do this with any whole power or any power. If I had done x to the p power and keep doing this, every time you look times rule, you just increase the power by 1, right? Ends up exponential always grows faster than a polynomial function if you go far enough down the x-axis. You can do the same thing. Any power function grows faster than a logarithmic function. So like you learn all these relationships of you want this type of behavior or this type of behavior. The way we do that mathematically is you take these limits and decide which one is bigger eventually. Yes.
What if you had something like 3 to the x over e to the x?
So 3 to the x over e to the x?
Yes.
You would rewrite as this. And this number is bigger than 1, right?
Yes.
That means it must go to infinity. As x goes to infinity. So this one is an exponential growth once you rewrite the base.
Gotcha.
That was a good guess on something though where they might tie. So when do they tie? What if I just put g of x is x cubed? Now you divide, you only get the constant that make the same. But I could have done something like x cubed plus x. Or usually the way this shows up is you get something like this, so there's a bunch of other terms, and then always says we only care about the first one. And we don't really care about the coefficient. They all behave roughly the same. Right. So there's a block in the homework that talks about it. We skipped over those problems, but definitely look over those. It's a very big computer science topic. This is the mathematical way to do it. Usually in computer science, I guess all these would be functions of n. It's the number of steps you need. But it all works the same way. All right. Let's do some examples. These look hard. So let's find the limit as x goes to 0 from the right. So x to negative 1 minus one over e dx minus 1. It should be worse than most of your homework. So, I never like negative exponents. It's always easier to write the fraction to see what's happening. So I get this. No reason to have a negative exponent sitting there. Negative exponents hide fractions, which is an issue when you're trying to find fractions. Like we need it in fraction form. So what happens here? It would be 1 over 0 plus minus 1 over e to the 0 minus 1. What's 1 over 0 plus? Infinity? And this one's going to be e to the 0 is 1, right? it's infinity minus 1 over technically 0 plus again. So this one is technically infinity minus infinity. Do we know the answer? It's similar to the question we just had. When you want to decide if f is bigger than g, did we look at the subtract, like, did we look at the difference or look at the ratio? Why would we pick ratio over difference? If f is bigger than g, so think about it this way. If this one is a lot bigger than this one, this has to go to infinity, right? This first one would win. If this one is a lot bigger, subtracting it would win, this would go to minus infinity. But just looking at it, do we know which one it is? So this is again that question of which one is bigger, the one that comes first or the one that comes second? And there's a reason we say f is a ratio, it makes the limits more easier. Saying f is a difference, it's sometimes hard to know which is which. So we need to make this a fraction if we're going to actually do this. How can we do that? Yeah.
You can multiply the denominator of the first fraction by the second fraction, and then the denominator of the second fraction by the first fraction. So that way they have the same denominator, and then you can combine the fractions.
Did I get that? Take
Yes.
two bases, multiply them. So do 1 times this minus 1 times this base. So combine bases. So now I have a single fraction. So before it was indeterminate, I haven't really done anything, so it's still going to be indeterminate. You might want to check. If I were to plug in, I get this. So e to the 0 is 1, so 0 divided by 0. I went from infinity minus infinity to 0 over 0. It's still indeterminate.
Yeah,
I haven't canceled or really done anything, I just rewrote the problem. Until you cancel, if you start with indeterminate, it's still going to be indeterminate. So what did that accomplish?
well, now you can use L'Hopital's rule.
Now it's a fraction. So most of this section is it indeterminate, yes or no? If it's not indeterminate, you already know how to find the answer. So then the case when it is indeterminate, what do we need to do? We need to rewrite it to make sure it's a fraction with the right form. That's how we're going to start all of these problems, unless you just know how to find the limit. Some of these, in theory, you know how to do it from section 1-6. So if you already see how to find the answer, just use that. Alright, so this one is indeterminate. What should I do now?
L'Hopital's rule.
I can do L'Hopital's rule. It's 0 over 0. So L'Hopital's rule says this is the limit is x to 0. What's the derivative at the top?
E the x minus 1.
E to the x. Derivative of negative 1 is 0. Derivative of negative x is negative 1. Thanks to chapter 2, you earn the right to just write something like this. Okay. You can always show more steps here. So I'm kind of showing less steps on the board than I would for taking a derivative necessarily. Now that we're in chapter 3 with the idea of you're allowed to show this type of work and not show more steps. If you're comfortable doing it, you can get the right answer. If you need more steps, definitely show it. Okay. What about on the bottom? I want to take that derivative.
You need the product
You need a
rule.
product rule, unfortunately. So, what is that? X, what's the derivative of the second one?
E the x.
E to the x minus 0 is e to the x, plus derivative of x is 1, that's e to the x minus 1. So I I end up with limit as x goes to 0 of e dx minus 1 on the top, and what do I end up with on the bottom? X e dx plus e dx minus 1. There's no connection to this stuff I'm doing, right? Alright, am I done? What do I do now?
You check to see if it works now by plugging it in.
Check to see if it works. We did something, right?
Yes.
Anytime you do something, the next step is check to see if it works. So, I try to plug in. E to the 0 minus 1 over 0 plus e to the 0 minus 1, 1 minus 1 over 1 minus 1. It's still 0 to 0 point. So am I done?
Right.
Something still has to cancel, right?
You gotta do it again.
Yeah, it looks hard to cancel. Let's do it again. Technically, we know how to do this one. Maybe. It's been a long time. So, I don't know. Lay it out, do it again. So, the top immediately looks better, right? So what happened for the numerator? I started getting rid of all these extra things like this 1 and this x. Eventually it's just e dx. Why did that make sense? That's really the term that matters the most, right? E dx is going to be the more interesting one that kind of dictates behavior here. You have to be a little careful of that statement going to 0. If I go to infinity, that's definitely true. Going to 0, you might not have good intuition. What about on the bottom? Still
Yeah.
be product rule?
Yeah.
So I get x times e dx plus 1 times e dx plus e dx plus 0. Okay. For e dx. Yes.
Couldn't you cancel the e the x at that point?
At this point,
Yeah.
yes, I could. And if I go into infinity, I would. Because right now, e dx is in everything, right?
Mhm.
So I'll do this two different ways. Your comment was this. Like, we always have factor cancel, right? We don't want to forget the fact we can do factor cancel. Like, we still have 1, 5, 1, 6 sitting in the back of our mind, hopefully. So, since everything has an e dx in it, divide everything by e dx. I would get that. And it's because technically I have an e dx here and an e dx here. So they cancel. Factor that one out of the top, factor it out of the bottom. You're left with these. Now what happens? Just plug in, right? I get 1/2. Technically I could have done that before. Why? At this point, if I tried to plug in before I did any more work, I would get this. E to 0 is 1. So I technically could have plugged in. I didn't need to cancel more. If I wanted to, I could. It didn't really hurt anything. Yeah.
So would you have been able to cancel in the step before the one we just got to?
And
Like
this
that.
step,
Yes. Would you
maybe
have been
I
able
have
to?
to cancel e dx minus 1.
Oh, okay.
Which means this is going to be a little bit harder to factor.
Okay.
So the nice thing about L'Hopital's, right, anytime you do L'Hopital's rule, technically you're doing factor cancel, but it's very much behind the scenes. Yeah, here it wasn't immediate how to cancel without trying to factor the bottom in some way. Like I couldn't just cancel e dx, right, because that minus 1 is still sitting there. So if I'm going to cancel, I need to factor out the entire expression up here. The whole thing is what's giving me 0. When do you factor cancel? It's when you have 0 to 0, basically. In order for that top part to be 0, I need the minus 1 part to make it factor right. Okay. Any other questions? Yeah, that one looks, all these can look bad or good, just depends, I guess. Always want to keep in mind where you're going. And like, always kind of plug in, make sure, can I stop at this point, or do I need to? It's easy to lose perspective. Alright, I have several more examples, but y'all came to class today. Don't want to ask about a homework problem or anything?
33.
33. You are always prepared to ask about a homework problem. And I always check to make sure it's assigned. Oh, that looks awful. Let's see why I asked that. So I always pick the problem I'm going to grade before I let you ask questions so that I can't purposely grade this one or not grade it. So this really is shot in the dark for you. 33. Limit as x goes to infinity of x e to the x divided by e to the 2x plus 1. There are better ways to do this. Alright, so if I try to plug in I get infinity over infinity form, right? So what should I do? Yes, usually we do Lopez. This is what I think would be easier without Lopez, but we seem to be on a roll with Lopez, so we'll do Lopez. So if I do Lopez rule, let's see, x times e dx plus e dx to the top, doing the product rule. And at the bottom, I get what? E to the 2x times root of 2x, which is 2, plus 0. So I get x plus 1 times e dx divided by 2e to the 2x. Yeah, technically this is still infinity over infinity, right? So I like what you said to do. Since it's infinity over infinity, I could keep doing L'Hopital's rule. And that would be multiple product, right? I need the product rule and chain rule stuff on the bottom. And you kind of keep going, right? But what did he say to do? I could just cancel out e to the x to start. So this is one where I probably, instead of just continuing to do L'Hopital's, eventually I want to get rid of this e to the x. So this one you can really, before I couldn't easily divide by e to the x because of this term. That plus 1 was sitting there. Here I can. So how do I think of e to the 2x? Really e to the x times e to the x. So that means if I had to cancel out 1 power of e dx, on the top I get x plus 1, on the bottom I get 2 times e dx. Right? It helps you write that step in there. I was canceling out e dx. I had e dx in the top and the e dx in the bottom. So now what do I wanna do?
You have to do. You still have infinity over infinity.
Yeah, it's still infinity over infinity, right? Which one do I know is bigger? Top or the bottom? Bottom? Exponential beats polynomials, what should my answer be? 0? So that is very much kind of hand wavy. Please show steps like on your work, but that is a way to guess what the answer is and then see if it makes sense. So here, if I do love capital again, I get the limit as x goes to infinity. 1 divided by 2 e to the x, which is now 1 over 2 times infinity. So 0. What's that below 1,000? 6 is the numerator. These are always interesting because you don't know how many times you'll end up with L'Hopital's rule. Or we did the example last Friday where you moved the wrong one. No matter how many times you do L'Hopital's rule, the problem's not improving. Like there was one choice better than the other. And several of these problems, it doesn't matter which choice you make. Both would work. But there are examples where one choice is much better than the other, kind of like we did in class last time. On the quiz Friday, it'll be 3-1 and 3-6. 3-6 will be 2 or 3 problems where one of them definitely don't use L'Hopital. Can't promise that you haven't heard the quiz, but I plan to do. Part of what you want in this section is when do you use it and when do you not. Alright, I'll see you all Friday.